In today's video, we will understand about D value, Z value and F value. These are the very important values, very important used terminologies when we are talking of sterilization. So let us understand one by one what is D value, what is Z value, what is F value, and all three are interconnected. There is no independent value. So let us first understand what is D value. So in simple terms, we will understand. I'll make you very simple explanation to make you understand that what is D value. So when I say D value of a specific microorganism is 2, just for example, if I say microorganisms D value is 2, then what does it mean? It means that if microorganism population is 1000, just say for example there is 1000 population of the specific microorganism, and I say D value is 2, then at specific temperature, let's say 121 degrees. So at 121 degrees, to reduce this 1000 to 100, that is reduction of microorganism by the factor of 10. If it takes 2 minutes, then we can say D value of that microorganism is 2 minutes. I'll explain again. When I say D value is 2, then at specified temperature of 121 degree, it takes 2 minutes to reduce 1000 microorganisms to 100. That is a 10 factor. That is a reduction by factor of 10. So that is we can call reduction by 1 log reduction. So 1000 is reduced to 10. Then it will say that D value of that microorganism is 2. Now let us hope this is clear. Now let us understand what is F value or F0 value. So there is a specific kill pattern. So microorganisms are getting killed not only when they reaches to the 121. That killing start, vegetative bacteria will start get killed at 80 degrees. So what is the overall exposure? What is the overall heat transfer to the microorganisms? It is calculated at F value or F0 value. For moist heat we use term F0, for dry heat we use term FH value. So what is that F value? So F value is the equivalent time of exposure at specified temperature. It is a time. F0 value or F value or FH value is always a time. It is not degree Celsius. So what is that? Equivalent time of exposure at specific temperature. So when I say 121, then if I calculate F value starting from 100, so what does it mean? That in the entire exposure from the temperature 0 to 100 to the completion of sterilization hold, what was the equivalent time of exposure? So it calculates each and every minute equivalent time. So if it is 100 degree per 1 minute, then how much? It's not simple calculation, but how much at 121 degree. If the exposure was for 1 minute at 100, then what is the equivalent time of exposure at 121 minutes? Same way, if it goes to 101, then what is the equivalent time of exposure at 121? If it goes to 102, so that is in that fashion the values is calculated. The F0 value is calculated in that factor, and there is an equation. You can search it out. I will not explain the equation now, but this is a very basic understanding that F value is the equivalent time of exposure at specified temperature, and it is always mentioned or always measured as a time. So I'll repeat again. D value is the time required at specified temperature to achieve 1 log reduction. So if my 1000 microorganisms are there, 1 log it's 100 in 2 minutes, then D value of that microorganism will be 2 minutes at 121 degree. F0 value is equivalent time of exposure at specified temperature, and it is calculated starting from 100 to completion of hold, or that values can be changed. That value will differ based on what base temperature we are using for the calculation, but specified temperature will be 121 degrees as a sterilization kill temperature. Now let us understand Z value. Z value is the number of degree of temperature change required to change the D value by factor of 10. So for example, my D value of a microorganism at 121 degrees is 2. If I increase the temperature by 10 degrees, so if I make the temperature 131 degrees, then D value will change by factor of 10. So it will become 0.2. I will explain again. If my D value of for microorganism is 2 at 121 degree, if I increase the temperature by 131, this D value will become from 2 to 0.2. So there will be 10 factors change. If I reduce the temperature from 121 to 111, then D value will become from 2 to 10. It will change by factor of 10. So this is Z value. If I change the temperature by factor of, to change the value of D value of a microorganism by factor of 10, the number of degree of temperature change required will call Z value. For moist sterilization it is 10. So if my D value at 2 is 121 degrees, if I increase the temperature by 10, 131, then D value will become from 2 to 0.2. And if I decrease the temperature from 121 to 111, the D value become from 2 to 20. So this is Z value. Z value for moist sterilization is 10 degrees. For dry heat is 46.4. So hope this small video will help you to understand what is D value, Z value and F0 value. Thank you very much for watching my full video. Hi, in this video we will understand about 3 important things about sterilization. First is why we need to remove air from the load. Second, how we can calculate F0 value for required sterilization. And third, what is an overkill approach cycle. So let us begin. Let us begin with why we need to remove air from the load. So presence of air limits the capability of steam to penetrate, limits the capability of steam to transfer the heat transfer coefficient. It depresses the temperature. So when air is present in loads such as silicon tubing, such as long hoses, such as rubber stoppers, such as filter housing, such as gowns, such porous loads contains air and it is very difficult to remove. If air is not removed, steam cannot penetrate and we cannot achieve the required sterilization temperature, required heat at all the locations of the load. So to remove the air, vacuum is applied. In hospital surgicals in the earlier days, vacuum as low as 15 to 20 mmHg, that is less than 0.4 psi was being applied for 8 to 10 minutes to remove the air. But even with this deep vacuum, there is no surety that all air will be removed. So to ensure effective air removal, instead of pre-vacuum pulse, very high pre-vacuum cycle, industry has adopted the cycle of vacuum pulses, where multiple vacuum and steam pulses are applied for effective removal of air. And this is better technique than only one pre-vacuum pulse cycle. So what is being done? Based on the sterilizer to sterilizer, the required deep vacuum and required steam pulse is applied. So first vacuum pulse will be applied, followed by steam. So in first vacuum most of the air will be removed and then it facilitates the steam penetration during the steam pulsing. So first vacuum pulse, then steam pulse, then another vacuum pulse, then steam pulse, and third vacuum pulse and steam pulse. After these 3 vacuum and steam pulsing cycle, it goes to the heat up phase and it ultimately achieves the sterilization hold temperature. It is maintained at required sterilization temperature, time and temperature such as 15 minutes or 20 minutes or 30 minutes based on the whatever cycle is designed, and it is maintained, and then it goes for the post vacuum and cooling. So this is how vacuum pulse facilitates steam penetration. This is why air removal is required, as air limits the capacity of steam to increase the temperature of load. So this explains why we need air removal, and it can be done by vacuum and steam pulsing cycles. The values of vacuum and the steam, like up to what extent the vacuum has first pulse, what extent to the second pulse, and what extent third pulse, as well as what temperature during the steam pulse has to be applied, varies based on the sterilizer to sterilizer. once we decided this importance of removal of air and steam pulsing cycle design, now let us understand how to calculate F0 value for a desired biological indicator or desired biological known load. So in my one of the previous video I explained what is F0 value and what is D value. So F0 value is equivalent time of exposure at specified temperature of 121 degrees, and D value is time required to reduce the bioload by factor of 10 at 121 degree. So my biological indicator strip is having bioload of 10 power to 6, and to make it 10 power to 5, if it takes 1 minute at 121 degree, then D value of that biological indicator strip will be 1. So how to calculate F0 value for a specific biological indicator? So if my biological indicator BI spores population is 10 power to 6 and I want to have 6 log reduction and D value is 1, then at 121 degree for 6 log reduction, if F0 value is 1, then 6 multiplied by 1 is equal to 6, that F0 value will be 6 at 121 degrees Celsius temperature. If D value is 2 and if I want to achieve 6 log reduction, then my required F0 value at 121 degree will be 6 multiplied by 2, that is 12. So F0 value will be 12. So I have to expose my cycle at 12 minutes at 121 degree to achieve 6 log reduction. So this is how we can calculate F0 value when we know the spore population of the biological indicator. Basis that we can calculate F0 value by this method. Now third thing, coming to the overkill cycle approach. So what is an overkill cycle approach? So if my spore population is 10⁶, and if I want to eliminate that 6 log reduction, then I have to run the cycle. In theory, considering the F0 value, in theory, if D value is 1 and I want 6 log reduction, then I have to run the cycle for the 6 minutes at 121 degree. However, in the sterilization practices, to sterilize goods, difficult to sterilize goods such as silicone tubing, filter housing, gowns, dense rubber stopper packs, filling assembly, it is usually adopted overkill cycle approach. In general, the microorganisms which are found in production area have the D value in ranging from the 0.5. So with 0.5, it is with even a 6 log reduction approach, even with 12 minutes of cycle, even with the 6 minutes of cycle, it get eliminated. But as an industrial practice, validation teams or sterilization experts, they prefer to go for the overkill approach cycle. So what is overkill approach cycle? For example, if my population is 10 power to 6, if my D value is 1, then 6 minute cycle at 121 will reduce the bioburden to the required, it will achieve 6 log reduction. However, in order to achieve overkill approach, normally it is being done the double the time. For example, if my F0 value is 1, my BI's population is 10 power to 6, then 6 minutes is sufficient, but they'll go for the 12 minute cycle, that is 121 degree for 12 minutes. So it will achieve 10 power to minus 12, 10 power to 12 log reduction of the BI. So with this approach, a better sterility assurance is achieved, and this approach is used when the goods are heat stable, such as tubings, stoppers, gowns, syringes, then filter housing. So if the load content allows to go for the higher time and higher temperature, then this overkill cycle is adopted. In this overkill cycle approach, we don't need to determine pre-bioburden of the load, because as I explained, in production area normally which are the microorganisms are found are having the values around D value around 0.5. So this overkill approach cycle will eliminate all the organisms which are usually found into the clean rooms. With this approach, better sterility assurance is achieved. We don't need to go for the bioburden study. We don't have to determine the pre-bio load of my load which I am going to be sterile. Another approach of bioburden I will be discussing in my next video, that is required especially for the terminal sterilization cycles, terminal sterilizers product, where product has certain limitations of how long they can be exposed to the sterilization temperature, and that is again comes from the F0 value and D value of the product. So hope this small video helps you to understand 3 important things about the sterilization. If you like, you can subscribe to my channel PharmaVen. Thank you very much for watching my full video. In this video we will understand about terminal sterilization of finished pharmaceutical products. In my previous videos I have discussed about D value, Z value, F0 value for the components, how it can be determined, what are the values. In this specific video, upon the request of one of my friend, I am preparing this video for the terminal sterilization of finished pharmaceutical products. So let's understand. I'll be covering 4 important topics in this. First is why air removal is not required in terminal sterilizer, why air overpressure is required in terminal sterilizer, what is the significance of product D value in determining the cycle parameters, and how we can develop a cycle for the terminal sterilizer. So these 4 important factors I will be covering in this video, so please be with me. So the products which are heat stable, the finished pharmaceutical products which can sustain moist heat, must undergo terminal sterilization. It is a regulatory expectations that if a finished product can be terminally sterilized, then it must be terminally sterilized. It should not be processed with aseptic processing. So that is a regulatory expectation behind that. So let's understand step by step. So for the terminal sterilizer, do we need to remove air? No, air removal is not required, or even it is not desirable, because anyways the container is going to get pressurized. So filled container, it can be vial, it can be bag, will have either air or nitrogen inside, and when it exposed to heat, the container, the liquid inside the container will get vaporized, the air will get expanded, so there will be steam air mixture inside the container and it will create pressure. So anyways, it is not about removal of air, anyway it's not about heat penetration, it is about transferring the heat as fast as possible to the container, to the liquid inside the container, glass container or bag container. So air removal is not required. On the contrary, the container itself contains air. So when we transfer heat, the inside liquid will get heated. The liquid will convert to vapor and it will get pressurized. And the pressure will be sometimes higher than the pressure inside the chamber. In this case, a very important factor comes in picture about pressure balancing. So when we heat the container, the liquid filled container, the pressure will be created inside which will be so high, it can be higher than the chamber pressure by the steam pressure inside the chamber. So there will be a tremendous pressure inside the container. To counterbalance that, we need external pressure inside the chamber. So air removal is not required. On the contrary, higher pressure is required, so that it will compensate the external pressure. So let's understand. So when we apply heat, the inner liquid will get vaporized, it will get pressurized. So if the container is solid container such as vial with stopper, then it can sustain that inside pressure. But if the container is like flexible bag, so that pressure will be so high. So if we don't provide counter pressure from the steam air mixture from the chamber, this container can burst. So that is the reason air removal is not required for the terminal sterilization product. Terminal sterilized product also undergoes rapid cooling. So in that case, when we are rapidly cooling, so the chamber pressure will drop faster than the pressure inside the container. In that case, if the vial, if it cannot sustain, then we have to provide air over pressure during cooling. In case of flexible bags, if it is a flexible bag, then it cannot sustain that rapid decrease in pressure inside the chamber, so that can burst. So in cooling phase also air over pressure is required. So in order to maintain the container's integrity, it is required to have air over pressure during steam sterilization as well as during cooling phase. So that's why most cases steam air mixture is used for the sterilization of the finished pharmaceutical products in the rigid container like vial or flexible container like bags. Now why air over pressure required, I just explained. To maintain the container integrity, air over pressure is required during the sterilization phase as well as during cooling phase when we are applying rapid cooling cycle. Now coming to the cycle time determination, time and temperature parameter determination. What are the important factors to be considered? So that is D value of product. So we must know what is the D value of product. There is a method called Bayer vessel method, and there are other methods. Using challenge organism, we can determine what is the D value of product and why it is important. So if the product is thermostable but it has certain extent, exposure to the temperature can impact product assay, pH, color, can impart particles into the product, can impart viable or non-viable particulate matter inside the product, can impact the stability, can impact the long-term stability of the product. So when we are heating the product, these factors are getting impacted. I will repeat: product potency or assay, pH, color, it can generate particles, it can impact microbial load, it can impact non-viable particle counts inside the product. So these are the important factors which has to be considered when we are determining the terminal sterilization cycle for the product. So D value is must to be known. Based on the D value, we can determine to achieve 6 log reduction how much F0 value will be required. Once we determine D value and F0 value, next comes the container mapping study, temperature mapping study inside the container. So we have container size specific, for example 50 ml container, 30 ml container, 100 ml container, or sometimes 1000 ml container. So we have to place sensors inside the container and see what is the temperature distribution profile within the container. So how it can be done? We have to place sensor at the various locations inside the container, top, middle, bottom. If the container is big, then more location has to be covered. How it helps? So container mapping study usually is done at the laboratory scale first to determine which is the hottest or coolest spot inside the container. Once it is determined, then we have to go for the chamber mapping. So we have to place the load and determine what is my containers within container coolest location. That is first. Second, inside the chamber, out of all my load, which container or which location is getting the lowest temperature? In that specific location, which container is getting the lowest temperature? How it helps? It helps to determine overall time, temperature and pressure requirement for the terminal sterilization of product. So three factors: what is the coolest location inside the container, what is the coolest location inside the chamber, and basis that we can determine how much time, how much duration, at what temperature we have to expose the cycle. Studies can be conducted at temperature like 112 degree, 180 degree and 121 degree, and basis that we can determine which cycle fits the best for the given specific product based on the D value of product. So this is another important factor for determining the time and temperature and pressure parameter for the terminal sterilization of the product. So once it is determined, what are other factors which are to be considered for the determination of for the thermal validation cycle finalization, to finalize the parameter for the thermal validation cycle. The first is container type. It is rigid wall container like wire or flexible wall container like bag. Then how many containers, what is the fill volume, how many number of trays within the load. This will determine what parameters has to be applied. Next will be the placement, surface contact time. So how we are placing the container, are they in the tray, are they directly placed on the container, on the shelf, are the trays are perforated, are the shelf are perforated, because this perforation is required. Why? Because there will be lot of condensation will be generated during the cycle, and we are not applying any vacuum in terminal sterilization product. We are not applying initial vacuum as well as post vacuum into the terminal sterilization product. So we need perforated trays and perforated shelves for the removal of condensate. So how is the placement? Are the perforations are big perforations, small perforations? Will it allow proper flow of steam and air throughout the chamber? What is the other important factor is what is the viscosity of the product? Viscous product may get more time to get heated. Less viscous or aqueous product like water based product can get less time to get heated. This depends on what is the content of the product. So viscosity plays another important role. Fourth point is how many number of trays inside the chamber and what is their orientation. So I have seen the examples by changing the if you are not getting the temperature proper inside the containers, changing the orientation such that it will facilitate proper flow of steam throughout the chamber, then you can get better orientation, better steam penetration throughout the load. So this is one more important factor. Another factor, fifth factor is what is your autoclave type? It is purely steam based, or it is steam air, or it is water flow based, or superheated water type chamber. So this also plays a very important role, that whether it is steam air mixture we are using, or we are using superheated water, or we are using only steam, because the vials are rigid vials and it will sustain the pressure or drop in pressure during the cooling cycle. So these are the important factors to be considered when we are determining our thermal validation studies. I will share one of the example which I experienced, that in one of the TS cycle load we are getting a very wide range of F0 value within the small chamber. So it was expected that in a smaller chamber the F0 value should not have a very big range, it should be very narrow range, very well determined range. So what changes we made? We made changes like this. We increased the perforation size of the shelf and tray to facilitate more steam flow. We created distance between the trays, reduced some of the number of the trays, so there will be more distance between two trays and there will be better steam penetration. The blower which was there for the steam air mixture inside the chamber, the blower capacity was increased. It was fitted with higher RPM blower, so it was better able to mix steam and air mixture inside the chamber. So with these changes, the range of F0 value came to narrow. What advantage it will have? It will have advantage that it will not impact the product quality, although it is within the required F0, but if you constantly maintain the value, then products CQS such as assay, impurities, any color change, pH will remain within certain range. It will remain constant. It will not have many fluctuation from one batch to other batch. So this is how it is advantageous to properly determine a terminal sterilization validation cycle. Hope this small video will help you to understand how we can determine terminal sterilization validation cycle. If you have any questions, you can put on the comment. I can answer within the comment, and I can make more video to further explain in detail. So thank you very much for watching my full video. If you like, you can subscribe to my channel PharmaVan. Thank you. Welcome to my YouTube channel PharmaVan, and in today's video I will be discussing about steam quality. Steam plays very vital role in steam sterilization, and it is very important that we should be using proper quality of steam. How we can measure quality of steam? How we can measure quality of pure steam? Let's understand. So there are three important acceptance criteria, measurement points, quality measures for the pure steam, and those three are amount of non-condensable gases into the steam, dryness value of steam, and superheat value of steam. So what are these? What are the acceptance criteria? Let's understand. Let's start with non-condensable gases. So what is the non-condensable gases in steam? Before that, we must understand how steam acts, how steam kills microorganisms. So when we heat water, it converts to steam. The amount of energy, amount of heat required to convert water into the steam is called latent heat of vaporization. So when steam condenses into the chamber onto the load, the latent heat of vaporization which was utilized, the energy which was utilized in converting the water to steam, that heat is now transferred from steam to the load items. So steam condenses onto the load item into the autoclave chamber and transfers that heat to the load. By that way, it increases the load temperature, and by that way it kills the bacteria. How steam kills the bacteria? It is because of protein coagulation of the bacterial cell wall. We know that bacteria contains DNA, it contains cell wall, it contains peptide protein molecules. So this protein is coagulated. Because of protein coagulations, the bacteria cannot multiply further, they cannot grow. So we all know that bacteria, how bacteria grows, they divide and grow. So one bacteria divides into 2 becomes 2, 2 bacteria divides into the 4 becomes 4, 4 bacteria divides becomes 8, 16, 32, 64, thus in these multiples they grow. So what pure steam does? It transfers its latent heat of vaporization to the bacteria and causes protein coagulation so that bacteria cannot grow further. If there is a presence of air inside the steam, which we call non-condensable gases, then what will occur? This air will act as an air pocket, or it will form a layer of air onto the load. How then presence of air can impact the sterilization? Let's understand. So air has a very less heat carrying capacity compared to steam. So equal amount of air and steam, the steam carries a much higher amount of heat than the air. So presence of air in steam restricts the capacity of steam to heat the load. It creates air pocket, patches of cool areas within the load. If it is a layer, it will not allow heat penetration to the load, it will not allow the latent heat of vaporization to transfer to the load. That way it will prevent the steam's capacity to heat the load to achieve effective sterilization. So if the non-condensable gases are present into the steam, they are nothing but the air which will not condense to water. So this air acting as a non-condensable gases limits the ability of steam. So what is the acceptance criteria for the non-condensable gases? So by testing, we condense 100 ml of steam to water. In that 100 ml condensate, the amount of non-condensable gases should not exceed 3.5 ml. So per 100 ml of steam condensate, non-condensable gases should not be more than 3.5 ml. So that is the acceptance criteria. And we understand that because of non-condensable gases, it is air and it will prevent the steam to impart effective sterilization. So one is non-condensable gases. What is next? Superheated steam. So what is superheated steam? So if steam contains lot of heat, all the amount of moisture into the steam will get evaporated. So there will be no any moisture into the steam. So it will act as a superheated steam, and superheated steam acts as a dry air. What is the impact of superheated steam? So superheated steam will not condense onto the load item. It will not transfer its latent heat of vaporization to the load item. So by that mechanism it will simply touch the load and travel, but it will not condense. If it not condenses, then it will not transfer the heat, it will not enable the killing of bacteria. As we understand, air has a very less heat carrying capacity. Same way superheated steam will not condense and it will not effectively heat the load. How superheated steam phenomena occurs into the chamber? So if with the same amount of steam present into the chamber, if pressure drops, then the amount of energy remains the same. So what happens if the pressure drops? The remaining moisture inside the steam will evaporate and that will act as a superheat steam, and it will not transfer, it will not get condensed, and it will not provide effective sterilization to the load items present inside the autoclave chamber. So this is how superheated steam is important. If steam is superheated, it will not achieve effective sterilization. So what is the acceptance criteria of superheated steam? So superheated steam should not be more than 25 degrees Celsius above the boiling point of water. I will repeat, superheated steam value should not be more than 25 degrees Celsius above the boiling point of water. If it is more than that, then there will be no moisture, it will act as a dry heat and it will not achieve effective sterilization. So this is superheated steam. What is third point? Dryness value. Sounds strange, like how a steam can be dry, but yes, we need saturated steam for the effective sterilization. We need dry steam for the effective sterilization. So if there is lot of moisture inside the steam, then what will happen? Because of presence of lot of moisture, it will not be a saturated steam, it will be wet steam. So the amount of heat contained by the dry steam, in moist steam, it will in the wet steam, the amount of heat carried by the same amount of steam will be less. There will be lot of water droplets inside. So what will happen? When the steam gets condensed, there is a lot of water. So water contains the less energy, less heat energy than the steam. So when the steam condenses and it contains lot of water, then it will generate lot of condensate, but there will not be enough heat transfer to the load. And we know we need heat transfer from steam to load to achieve the effective sterilization. So if steam contains lot of water droplets, then it's a wet steam, it's not saturated steam, so it will not achieve effective sterilization. So for that we need dry steam with enough of moisture so that it will travel, it will condense and it will transfer the latent heat of vaporization to the load. So what is the acceptance criteria for the dryness value? So dryness value should be more than 0.9%, 0.90 for the normal loads and more than 0.95 for the metal loads or hard loads. So if we consider 1 as a value of dry saturated steam, then we need 0.9 value for the normal loads and more than 0.95 for the metal load. So this is the dryness value. So we understand three important factors: non-condensable gases. If there are a lot of non-condensable gases, then there is air and it will prevent the achieving, it will create air pockets and will not achieve effective sterilization. If we have superheat, then steam will act as a heated air and heated air will not have enough heat carrying, it will not transfer the heat from steam to the load and it will not achieve enough sterilization. And if dryness value, if steam is wet, it contains lot of water, it will generate lot of condensate, but it will not achieve the enough required sterilization temperature within the load. So this is how these three important steam quality testing affects the sterilization efficacy, affects the ultimate outcome of sterilization, affects the killing of microorganism affects the achievement of the required sterility assurance. So hope this small video will help you to understand the importance of steam quality. Please be with my channel, subscribe to my channel if you are liking my videos. Please also share to your friends to help me share the knowledge. Thank you very much for watching my full video.